All right, good morning. So I have I opened up the MATLAB script that I had written the other night and put it up here for you just to kind of show you what I did, and I'll pull it up in MATLAB in just a moment. This is just kind of follow up to what we were doing in class to show you slightly better code that it works. And I've gone into the MATLAB training stuff, thought a little bit more about that, and probably should bring up the syllabus. My plan right now is to essentially have this MATLAB term project consist partly of the trainings you'll need to do along the way, and you've already done one of those. I've put up another assignment. This one's, I think, 2 or 2.5 hours, whereas the first one was 4 hours. So recognizing these do take at least that much time, right? So I'm going to assign a homework as well. I come back and talk about that in a moment. But also along the way, these MATLAB assignments. So what I plan to do is give you, in addition to the course, like self-study courses, give you small assignments, like make this type of a script to say, okay, produce a figure and upload that also. So that'll be a small component, all of that alongside the homeworks. I'm going to keep those simple enough so that you're not tasked with like 20 hours of homework for this class per week. So I don't want to do that. So let me know if things are feeling out of balance. Okay, before I get there, let me just talk about the homework real quick. I've not posted it yet. I'm still working on that, in part because I realized the book that I was following doesn't provide any problems aside from the examples that we find in class sometimes. So I will be bringing in that other book, Benzonic or Brezonic and Arnold. So I've got a few slides that have some of that content. They have problems that look a little, well, they have problems first of all, which is nice, but they look like a good composition for us. So I'll be getting that to you probably by the end of tomorrow. Okay, so you can expect that, and you can see today on Moodle the next MATLAB learning assignment, and I'll likely also post some sort of a MATLAB do something assignment to post. Will be relatively small, but those will all come together into, I'll pull up the syllabus and my concept for that project so far. I'll go ahead and pull that up. So you can see my concept for that portion of your grade will be one part doing those completions, like you did the first time, and that'll be 40% of your term project grade. I'm going to add some small graded coding assignments, say, hey, upload your script and show me the figure that you made or something like that. Might add in a little bit of Excel there as well, just see a little bit of both. It'll kind of be like homeworks beside your normal homework, building up into this term project grade. And then the last part, I haven't decided exactly what that will look like, but it will be slightly more involved. Okay, code this thing, maybe show me a graphical user interface or something, like prompt, okay, input the pH, input the temperature, and then it calculates this, that, or the other. Something along those lines, because we're going to have both exams, and then you'll have plenty of time and no final exam. You'll have time for that, is the plan, right? So just as a, pull up the syllabus. This term project is what I'm talking about. We'll have either 3 or 4 homeworks. Maybe I'll put this down to 3 because the term project will kind of incorporate some other homeworks along the way. Okay. I haven't yet updated this, but I need to update for the missed class. We took a little while on some of the things, and I think we're going to go a little quicker today through some of the acid-base stuff. So I think it'll be all right. If we need, we just won't cover quite as much stuff for the first exam. Okay. Any questions on that so far? Okay, I will give you more info as I think about the final project a little more, but it won't be something that, well, A, we're building towards it, just doing the trainings and the small pieces, and B, it's not going to be something that you need to be working on in other ways today, right? So that's the plan, because you are working on it with the MATLAB already. Okay, so just real quick then, we'll go ahead and show you the script. So last time we left off when we were working on this other one, and now I think it was, I named this one. Okay, so I need to put myself in the right location. Let's see. Oh wait, they're already right here. Maybe it's this one. Okay, let me try it. Sorry. Okay, so when I run the one that I showed you on the PowerPoint, this is the result. And what we're looking at really is, and of course I haven't labeled it, that's something that we ought to do with a little more time and coding and everything, but what you see is this is going to be the pH scale on the x-axis, right? So 0 to 14. And that means the thing that we have more of as the pH is low should be H+. Right? So it should be H+ versus OH-. This is on a simple plot here that's scaled from 0 to 1. And down here, this is on a log plot, so we can kind of see a little more clearly how far down it goes. And we notice that the OH gets pretty much down to 10 to the minus 14th as it approaches 0. Likewise, the H+ gets down to about that as we approach 14. So this is just to kind of demonstrate the type of stuff we can do. You've already done some graphing, but I wanted to give you like, hey, here's pH versus something. And we can do that. Now we can also calculate this in Excel without too much trouble, right? So one thing I think what I'm going to give you next is to say, hey, basically do this. Maybe I'll select some other equilibrium. Do it in Excel so you can prove to yourself, okay, yeah, I could do this, refine those skills a bit, and then do it in MATLAB as well. And you know, not spending a crazy amount of time, but just practicing those pieces, coding it yourself. And if we want to get fancy, well, we'll get fancier over time. That's the plan. All right. Any questions, thoughts on that? Does that feel good plan-wise? Okay. So you can see Moodle for the next assignment. Essentially, this is the core MATLAB skills, I guess a cluster of courses, and what I've assigned is the first 2 of those 4. So I think the 4 together is like a 5-hour block, and so I asked you to do the first 2 of the 4, and then we'll go on. So I think one of those covers for loops, or that might be in a different setup, but you'll be building these components. And do let me know if you're in the middle of it and you're like, we already did this in the other one and this is like useless. Feel free to skip a bit and just let me know, email me or something, say like, hey, this was a waste of my time, so I kind of skipped ahead and I have 80% completion. With that explanation, I'm fine with that. All right, so we will be talking about acid-base chemistry and the electroneutrality equation today. It's the plan. So we kind of know what acids and bases are, but I really wanted to take today's lecture to elaborate some, to remind us of a few particulars, and to really just have an appreciation for where all acid-base stuff where all the reactions are important. So throughout aquatic chemistry and even non-aquatic chemistry circumstances, acid and bases are quite important, especially so with water, but it's not exclusive to water. So a few examples here, a couple tables we can look at. Table 3.1 in the book is a large vertically oriented one, so I didn't bother copying that over and doing that yet, but it's a good one to look at different acidity constants. I took a different table from another book, so we can look at a few there. Could be a good reference table. So that's all at standard temperature pressure, 25 C and 1 atm. And what we'll find is in so many of our equilibrium reactions or other reactions, the pH is kind of controlling the system to a large extent. So a lot of people have called the pH scale or the fact that pH is negative log of H as the master variable. So we'll see that quite often. It's just a generic term, and not every single equilibrium reaction has H plus in it or OH minus, but we just see it so often that it is so often controlling what's happening. Something is almost always related back to, okay, what is the pH? Okay, and then we also have table 3.2 that shows the dissociation of water at different temperatures, and I think I've got that up here, so we'll take a look in a few minutes. So a few examples of where acid-base reactions are important, well, or the proton rather is important. Obviously acid-base reactions. So we've got several listed here, pretty self-explanatory there. It ranges from ammonia situations to organic acids to inorganic and the carbonate system and stuff like that. Another one would be complexation reactions. So if we're looking at how iron, for example, is complexed with water and hydroxide groups, and how copper might do the same, well, that's going to require the removal of a proton from water in order to do that. So the pH then is quite important there as well. So those are one case where it's important. Dissolution and precipitation reactions. Again, this is not for every single case of precipitation, but in many cases, acidity will determine how likely or unlikely something will dissolve or precipitate. So in the case of this calcium carbonate, if we have calcium carbonate and acid, we end up getting calcium and bicarbonate. Now, that's something you've probably recognized before if you've done any type of mineral testing in a geology lab or something. You say, oh, okay, what kind of mineral is this? It looks this way, it feels this way, it has this kind of hardness. Oh, okay, so maybe it's one of these things. Let's put some acid on it and see what happens. And if it fizzes, you notice, oh, okay, that must be calcium carbonate, limestone kind of stuff. So that's a common one we see. And kind of probably recognize it in a lot of cases. Making something more acidic can cause things to dissolve, or in some cases maybe making it very basic. So redox reactions are another one. Transfer of electrons in a solution. You can almost think of the proton as the inverse of an electron. So it kind of makes sense that it's going to be quite prevalent anytime we have redox chemistry. Again, not every single reaction, but it's quite often. Gas and gas-water partitioning reactions, specifically the carbonate system. I think there might be some others, but the carbonate for certain. When we dissolve CO2 gas, we end up getting the carbonic acid, H2CO3, which is then has the acid-base equilibrium. So by manipulating the pH of something, you can get more or less CO2 to dissolve. Right? This is why we put phosphoric acid in soda, so that it will keep a lot more CO2 and make it fizzy when you drink it. Right? So if you look on a bottle of Coke, you'll inevitably see phosphoric acid. Some, if you look at some specialty ones, maybe they'll use citric acid or something, or maybe a combination. So that's important there. And then adsorption reactions. Something we're probably not going to cover too much in the class, but anytime you have a surface, the surface chemistry there is going to be important. So there's part of that would be maybe the charge at the surface, but also perhaps you're just going to release a proton because you're substituting in something else and it's kicking it off. Or backwards, vice versa. Okay, so it's quite important. A lot of systems, a lot of circumstances. We kind of already knew that, but I just wanted to give you a little overview like, hey, look, it's showing the proton is showing up everywhere, right? All sorts of places. Okay, so a couple useful tables. I mentioned 3.1, also not shown here. That has quite a lot of information. 3.2 here, this is temperature dependence for the dissociation constant for water, Kw. So if we stop and think about it, we almost always consider water when we do like the equilibrium reaction of water itself to figure out pH versus pOH, so the amount of H or OH minus. We almost always think 10 to the minus 14, right? It's the pH scale is up 0 to 14, so it's like, oh, it's always 10 to the minus 14, which is basically what we see when we get 25 Celsius, right? Maybe just a tiny bit off, 1% off of 10 to the minus 14. So we often just say, okay, it's 10 to the minus 14. Well, look what happens if we go all the way down to near freezing temperature. It's about 10 times smaller. So in fact, if we stop and think about it, that's going to change the amount of, it's going to change the balance. That's going to change the amount of H plus and OH minus in that solution, and it's going to change how much of either we could have. Likewise, if we heat it up 25 degrees instead of cool at 25 degrees, we get a situation where we're about 5 times larger in terms of the Kw, well, the magnitude. So correspondingly, that's another change. So of course, we can derive this from the definition we had talked about in previous lectures. Log K is equal to this this equation here. Actually, I'm not sure if we derived that exactly, but it's related to all the Gibbs free energy stuff that we talked about, right? So we have this equation where we could solve for that at any particular temperature. So looking at it this way, we kind of see, oh, this is quite important when normally we might neglect it in more general circumstances. Okay, I have another table here, 7.2 from this other book, Brezonic and Arnold. These are pKa values for several different acids. We're going to come back and look at this in terms of the first dissociation constant. Where does it arrive? How does that compare to how does that define a strong acid versus a weak acid, things like that. But there are more than this. We can see some of these acids, hydrochloric acid, for example, has a pKa of some negative value. So you would have to have a negative pH before you ended up with HCl remaining in solution. It's going to almost all, well, practically all be H plus and Cl minus. So kind of getting ahead of myself here, but that means it's a strong acid. It's going to dissociate in water, and you're not really going to be able to force it. You're not going to be able to add enough H plus to have a backwards reaction to HCl. That's just not really going to go left because that pKa is so negative, or is less than 0. Okay, so a bunch of acids there we can take a look at, and some of them we would call diprotic or even triprotic. You could even call the ones like HCl as monoprotic, just meaning one proton, or 2 for diprotic, right? So that's fancy terms we can use if we'd like to. And what we'll notice is we'll have a different pKa at each transition between a proton leaving or arriving. So phosphoric acid, for example, we have the first one at 2.15, and the next proton would leave at 7.2 pH, or it would reach equilibrium there. Okay, so a few definitions for our acids and bases, and we've likely seen these before in Gen Chem or elsewhere. So one of the first definitions of, okay, what is an acid was Arrhenius, and he said that, well, acids are substances that release protons in water. And the key there is in water. So other definitions that have come later have broadened that and said, well, it doesn't have to be in water. It could just be a proton donor somewhere else. So it's a good definition and, of course, relevant for what we do here. But we could go further and say, well, what about a Bronsted acid being any generic proton donor? And then that would mean a Bronsted base would be a proton acceptor. We get the concept of conjugate bases and conjugate acids from this thought process here. So a conjugate base would be whatever is formed when you release that proton. So the Cl- in HCl would be the conjugate base. And if we stop and think about it, Cl- is pretty happy just being by itself. So it's not likely to take back that H. And so it's a pretty weak base. Is kind of how that would work. So a strong acid would correspond to a weak base. Conjugate acid, likewise, if we're taking a look at something that's basic, would be what's formed when you accept a proton. So if the Bronsted base is a proton acceptor, then we can consider the reaction with ammonia, where we have NH3 plus H plus in equilibrium with NH4 plus. So ammonia can accept that proton, and that's why it's acting as a base, taking away protons from solution and forming ammonium ions. So that's kind of a descriptor of really the description of a base, and the NH4 plus is the conjugate acid in that sense. Now, I'm not going to go really into this today, but we can look at the equilibrium constants from a base perspective, so Kb instead of Ka, Ka being acid. It doesn't actually matter too much which one we look at, Ka or Kb, because we're just going to be looking at the OH, a reaction with OH minus instead of the reaction with H plus. And so they're just kind of inverted, and if you know one, you could know the other because we have the Kw. So I'm not going to go there, but the this other book, Brezonik and Arnold, does talk a bit about that. So if you're interested or need to know something about that, you can take a look. But it's not really anything particularly new. Okay, so then we also have Lewis acids and Lewis bases, and these are defined by the electron that's transferring it, or that's being accepted or donated. And if we think about it, the proton is kind of like the inverse of an electron. And so if you're exchanging a proton, that also means you're exchanging an electron. If you accept a proton, you're kind of giving that proton that didn't have an electron but wanted one, you're kind of donating an electron to it as you form something. So this NH3 going to NH4 plus, you can, and I think the book I might have brought this along, we can write ammonia this way, and the nitrogen here has an unpaired set of electrons. And so then when we add the H plus that doesn't have electrons but might like to, when this goes to, we could say NH3 with another H, we've just added that bond, kind of donating those electrons. And so a Lewis acid is something that's accepting the electrons, and in this case, the acid would be the H+. It's accepting electrons here. So these this would be the donor, and this would be the acceptor. So it's just another way to say and phrase the same concept in a way, but it also takes us out of the realm where it must be a proton. So we're talking about protons here, but in fact, sometimes there are conditions where it's not actually a proton that's doing this acidity basic type of action. So we can say then that all Bronsted acids or bases are Lewis acids, but not all Lewis acids are Bronsteds, because Bronsted is explicitly about the protons, whereas the Lewis doesn't have to be a proton. Some other thing can take that action. So that difference is it's not always about the H+. Okay, so they provide an example here saying, and again, this is using ammonia, where we have ammonia, and there's the paired electrons here, plus boron trifluoride. And the boron trifluoride here, I mean, I guess in the example I gave here, we do have a proton, right? So that's both a Bronsted and a Lewis acid. But this one, instead of a proton, so what we did have here, we're doing the BF3 instead. And so this unpaired set of electrons is going to react, and we're going to get a bonding here between the ammonia and that boron trifluoride. So once we do that, then we have had a essentially an acid, but a Lewis acid, and then this is a base. The same type of reaction has occurred. We've done that electron accepting or donating action, but without the proton as the driver. Okay, so I think this may occasionally be interesting or useful, especially with like metals, is what it's saying. So we might see some more of that. Metals tend to have that redox chemistry that maybe they can donate or accept electrons. So I think we might see some more of it there, but just wanted to give you an overview of the different classifications of acids and bases, why that's going. Okay, so let's talk for a minute about the strong versus weak acids and bases. So really it's a question about whether or not they're going to fully dissociate in water. I suppose maybe you could consider it in some other solvent, but we'll just stick with water. So a strong acid then completely dissociates in water, and that kind of means that it's got a pKa value that is quite low. In fact, we can define the weak acids as they're not going to fully dissociate because they have a Ka for this reaction that's 3 or higher, is kind of how they describe it. So if you consider making a solution of highly acidic water, then your pH is very, very low. At that point, if your acid is completely dissolved or like completely dissociated into its components, then that's a strong acid. It's kind of the way to think about it. Okay, so then mentioned this already, but the conjugate base for a strong acid, it's always a weak base because it's not going to take back up that proton very easily. Right, so the example was HCl would technically be in equilibrium if it could ever go backwards with this, but the Cl- is a very weak base because at no pH is it going to grab back up that H+. Okay, another thought here is that we can also define the proton, instead of as just H plus, we could say that this and water has some equilibrium with H3O plus. That's hydronium ion. That's another way to describe base, and we've got some discussion about that in a moment, where some people say, well, there's not really any H plus in solution, it's all this hydronium ion. Regardless of what we say about it, one thing we can note is that the pKa for this reaction, so the pKa here is 0, and that kind of defines the limit of acidity for water. So that means that any pKa lower than that for some acid is just going to cause the formation of this, which is effectively protons. So it's a weird way of like, and I think the book calls it the leveling effect of water. Any acid that was going to try to lower the pH below 0 will ultimately just cause formation of this, and you're not going to get a pH lower than 0, is the deal. So it's kind of a limit in that sense. Okay, so this hydronium ion is very related to H+, if not the exact same thing, as we'll talk about here in a moment. Okay, now if we take a look, we will look at that table again, but think about it and think about where the pKa's were listed, and I have the full table on the next slide, I think, where we'll see, all right, not just those first few where the Ka was greater than 3, or excuse me, most of those were less than, but several others would eventually be greater. So we can define everything down to the phosphoric acid, at least this first portion. All of these would be strong acids, and then as soon as we get to citric acid, we're starting to get to a weak acid, right? Now this is very close to a strong acid, so maybe it's, I mean, I guess by definition this is weak. And I believe we would treat phosphoric acid, H3PO4, as strong, and then the next two as weak, as the diprotic and triprotic, or excuse me, monoprotic. So this here should be strong, according to our definition, and both of these would be weak acids. Okay, so we can see there's quite a few examples here, different acids that we might see going all the way down to a pKa of 10 for phenol. So if we're using phenol, it's technically, it could lose that H+, but you have to have a very basic condition in order for it to do that, right? So we'll see this in many molecules, especially if we take a look at different organic molecules. There's often this OH group on it that could have that H+ leave. Could be a proton donor in that sense. But based on whatever particular pH we're at, maybe that's not going to happen, or maybe it will partly happen. You know, we'll have some portion that dissociates. So we can see that in many places. You can see the carbonate system is driven largely by the 2 pKa's for carbonate going to bicarbonate, and bicarbonate to carbonic acid. So many relevant things here, probably useful, and this should all be at standard temperature pressure. So these are common, kind of typical values. Okay. Any questions about that? All right. So hopefully not anything super new, but maybe good reference here. All right. So what about that question about hydronium ions versus the H+, the proton? Like what's all this about? If you read one book, it says one thing. If you read some other book, it kind of says another thing. And I do like this about the book that I've primarily been following. It it does give a bit of perspective here to say, all right, well, we have this reaction that I mentioned. And if we do the equilibrium on that, we have the hydronium on top and the H plus on bottom and the water on the bottom as well. And it could potentially get a little confusing. So it's saying, how can one textbook say it this way and the other way, and everybody still comes out with the same answer, right? Well, the truth is neither is exactly correct. Perhaps most of it is hydronium ions, but like we know from that discussion about purity of elements and like trying to have, like when the activity goes so close to zero, it becomes very unlikely that we'll be able to separate that, right? So in essence, there's going to be some H plus, but ultimately it's okay to just symbolically represent both with H plus or with H3O plus. So convention then is just use H plus, right? So physically, whatever we can use to discern them, to understand it, it kind of just, that's what it is. It just makes sense to use H plus. On that note though, it's actually not even just H3O plus. Well, first of all, the note about we can't have truly zero H plus, even though some people argue, like the other textbook that I started using some said, well, H plus doesn't actually exist in solution, but I think that's oversimplifying. Perhaps it's most of the acid is H3O plus, but again, unless we had an extraordinarily high Ka, like infinitely high, H plus can't really go to zero. So there's going to be some of it, and it's just going to be in flux. In fact, there are other complexes, water complexes, such that we have the equation H with water, some number of waters, and a plus, and these little clusters can be the representative of an acid. We can even go as far as 6 waters sharing kind of one proton in a cluster. So we talked at some point about how water can cluster together sometimes. This is the type of thing we're talking about. So perhaps you could even physically say it that way. And maybe in a few cases where you're really looking at how water is structuring around some molecule, maybe that's important, but in general, we'll just call it all H plus. So perhaps you'll find some occasion where somebody's oddly interested in that, and that'll be that. Okay, so from there, I want to move on to our next chapter, the electroneutrality. And really what we're doing with electroneutrality is kind of the same type of thing we're doing with a lot of other governing equations, processes, and systems. What we're looking for is to have as many governing equations as we can find to solve systems that are complicated, right? So we're often looking for these types of things. The equilibrium constant is one example, so equilibrium equations. Electroneutrality is another one we're talking about now. Related to that, but I'm not sure, I don't think the book goes into this right now, but I'm kind of adding this myself. In geochemistry fields, we often look, and I think we should cover this later, but we connect electroneutrality very closely with acid neutralization capacity, so ANC. And the acid neutralization capacity is almost the same as like a proton balance or an electroneutrality balance, kind of a bit of a combo of them maybe, or maybe it's the same thing as proton balance. Regardless, what we're taking a look at is how much base does the solution have to offer in order to remove all that. So can be another one. Mass balance equations, so not just, I think mass balance would be, a proton balance would be a subset of mass balance in my opinion. But you see in general like a mass balance equations are one way to look at a system to say, okay, here's the governing equations from it. Okay, I apologize, I added that last one, moved the text down too much. Sometimes we'll have a system where we simply want to leave it in general terms, like the concentration, total concentration of A minus, which would be the acid, right? So I guess the conjugate base, I mean. So like HCl, the Cl minus would be the A minus there. So it's like the acid that has given up its proton. Na plus, Cl minus, all that. So whatever form we want to write it in, maybe we leave it in general terms that way and set up a balance in those terms. Or maybe we'll go exact and say, okay, this is 10 to the minus 3 plus 10 to the minus 4 minus this, that, and the other. But so we'll kind of see a little bit of both. And sometimes it's useful just to solve it without even getting into the particulars and say, oh, okay, so if we know the amount of this that we add, then we get a proportional amount of that removed or required or something like that. So we'll see a couple things like that. Now, I want to take a look at 6 different cases that will really explain and give us the ability to work with pretty much all of the electroneutrality equation any way we slice it. And so I'm just going to take us through these cases that the book describes, and then we'll take a look at a couple of example problems. But just walking through each of one of these will give us some appreciation for, okay, what does pure water look like? Of course, that'll be relatively simple. The charges in pure water, if we can achieve pure water, would be the H plus and the OH minus. So that'll be really simple. But then, okay, what does it look like when we add some acid? So again, HA here is referring to, it's written down there, of course, a proton, H plus, and the base, or I guess the acid that gave the proton, right? So that's what we're talking about when we say that. And A is just talking about sodium here. Instead of a proton, sometimes we might add NaCl, right? You can imagine adding table salt instead of HCl. What does that do to the equation? Well, in many ways it acts the same, but we're not adding the proton then, right? So we're going to look at these different pieces. B would be a base. So if we had, any sort of base filling in there, we would see it that way. I think this is supposed to be too. So we'll see each of these examples and how these come into play. So anytime we're adding something like this, it's typically going to be either something like sodium, where it's a positive charge, or it's going to be something like A, where it's going to be something like Cl minus. It doesn't have to be an acid, right? So NaA here, this would be a lot like adding NaCl, right? Where we've got the sodium and the A is a chloride, whereas this one would be like HCl. Okay, so that's kind of the way to think about it if we're going to translate it in some practical terms. Okay, and we could also think of the base, let's see, as some positive charge, right? So we could have, let's see, H2B. So here's a good one. So sodium, and I think that's supposed to be subscripted, apologize for that. CO3, so sodium carbonate, 2 minus. So the CO3 would normally have a 2 minus, and it would be balanced with a 2 plus from those 2 sodiums. So that's, I believe, what this is symbolizing. Or you could have, for example, H2CO3 here. So all that to say, and I guess we'll just finish it out here. So if we did sodium bicarbonate, then NaCO3 with another H. Okay. We would probably just write that as, I guess we'd probably just write it this way. Okay, So that's kind of the type of thing we're looking at, and we'll walk through and look at how the book discusses each topic or each case. So for pure water, like I said, it's relatively simple. We have water dissociation into H plus and OH minus. We have a Ka for that. It's going to be in every solution. It's actually kind of hard to get just pure water because CO2, if nothing else, likes to go into it. Plus our discussion about like how likely is it that nothing else has made its way in there. It's really hard to get something pure that pure. So it's going to be hard to find this, but if we did, we would say, okay, all of the positives have to be all equal to all the negatives, right? Or we could say 0 is equal to all the positive charges plus all of the negative charges, right? Or I guess minus the negatives, but you know what I mean. Put brackets. We have to do these calculations in concentration units, so we kind of have to make some assumption about the activity because the charge, we're counting charges. So we're going to do these systems in a molar moles of charge, essentially. Okay, so the essence of charge neutrality is quite simple. We have to have ultimately a neutral system, is the point, right? There is no such thing as an aqueous system that is out of alignment from neutrality. That means if we were to calculate something and we find that there's out of balance, then we know we've measured something wrong. And so you can use this if you're doing some sort of a study for a natural water to say, does our charge balance? If not, how far off are we? And that's something that geochemists would do as an exercise to say, all right, well, if it's 0.001% off, that's typical. Our measurements aren't perfect. But if we're like off by 1 mole of charge or something, you know, that's maybe kind of crazy. So very simple for pure water. How about for pure water with some acid HA added? So what we need to do then is add in any of the ions that we just included. So we're adding some H plus. We already had a term for H plus, and now we have A minus. Now, of course, we have this equilibrium constant for this guy. So when we start thinking about how are we going to solve the problem to say how much of X, Y, or Z do we have, we start realizing, okay, these Ks are going to end up being important if we put these things together into a larger system of equations to do some sort of solution. Okay, so now in addition to the H plus and the OH minus, we have A minus. So now we could write it as, you know, again, they're taking the approach positives are equal to the negatives. It's also fine to simply add this to the other side to say OH minus plus A minus minus the H plus. So you'll see it actually showing up in this form fairly often to say 0 is equal to this stuff and the acid and any other positives at the end of it. Okay, doesn't really matter too much the way we write it. The end result is we have a neutral system, and at this point we just added that A minus. All right, so how about if we add in a sodium with that A? So we'll still get that A minus. Again, the sodium chloride is kind of a good example. So it's going to be some salt with sodium and A minus, enters the solution, it's dissolved, and we're assuming here there's no chemical bond possible between the sodium and the A minus, so it just completely dissociates. So here the Na plus is kind of a spectator. It's not really going to react with anything. It was there to kind of donate that that H, donate the A minus. All right, let's see. At that point, now we have two cations, and we'll do Na plus H plus equals A minus plus OH minus. All right, the fourth case then, we have H2B. So we've got a diprotic acid, essentially. This would be like carbonic acid. And some of it's going to dissociate, but not all of it. So that's the complication here. That's why we have H2b. And so now we have two equilibrium constants because we have the equilibrium of H2b. We'll call this K1 here as shown. And then we also have, once we form this HB minus, we have a second one where that could then dissociate as well. So now we're adding several species into solution, and maybe in some cases, one species might be negligible, but it's better to just say, well, we don't actually know what pH this is right now, so let's put all of the terms. Then later, if we notice that, for example, when we do a carbonate system analysis, we might say, oh, well, we're dealing with a crazy, crazy high pH, so we're just not going to worry at all about carbonic acid. We can exclude it because it's going to be 0.000001. Like, it's going to be a really, really low number compared to everything else. So sometimes we can do that, but in general, let's go ahead and write everything out to say, all right, all of the positive charges are just simply the H plus in this case. We didn't add anything else with a positive charge. So we're going to set that equal to the HB minus plus 2 times the B2 minus. So the 2 here, when we're counting the charges, we have to account for the 2 times that number of molecules because this is just the concentration of that molecule, does not include the charge, right? When we report the concentration of B2 minus, that's like 10 moles of B2 minus. But how many moles of charge does that mean? It's actually 20 moles of charge, right? So we put the 2 out there in front. Yeah, so it kind of explains this here. Essentially, our concern is moles of charge. Okay, then plus the OH minus, of course. Okay, so then whenever we have any sort of diprotic or triprotic acids involved, we're going to end up having each component that it could be, right? So in this case, it's H plus equals HB minus plus 2 B2 minus plus OH minus. All right, case 5 is NaHB, and it's very similar, except now we have the Na plus. There's not a whole lot to say there. Again, that sodium bicarbonate is a good example. We're still going to need each piece here. And finally, if we have Na2B, ultimately we end up with the same equation again, because we do have sodium there, and we do have H, and we do have OH, and B is going to be in equilibrium with those, so we can expect that we'll have B2 minus involved and HB minus involved, right? The H2B is not charged, so we don't have to worry about that, right? So it's not part of the charge equation. So ultimately, this is the same as the previous case. Nothing else really to think about. So now with that in mind, we have some tools here to say, all right, what does the charge neutrality look like? How do we get there? So let's have a bit of practice. Let's very, very simply write the general electroneutrality equation for a solution of pure water plus some NaCl. All right, so hopefully this was just getting the cations on one side, Na plus and H plus, and the anions on the other, Cl minus and OH minus, right? So nothing else really happening here. Okay, so let's do something a little more complicated. Give you some things to think about here. It's simple in the sense that we're just going to write out the chemicals again. And remember, if there's any charges, like a 2+ charge that you have to account for, take that into account. And do your best here. So the problem says, more complex solution, we have H plus, Na plus, K plus, magnesium, calcium, iron, FeOH2 plus, FeOH2 1 plus, acetate ion, OH minus, HCO3 minus, CO3 2 minus, Cl minus, HSF4 minus, sulfate, and FeOH4 minus. You can just use A minus for acetate. All right, so hopefully it kind of makes you stop and think a little bit like, is there an equilibrium that we're missing? You know, did I get everything? I think they kind of gave us just about everything. The acetate ion, they said, can just be A minus. If we had H A minus, then we would need also a 2 minus because that H could leave. But otherwise, I think they were pretty thorough, just gave us everything. So I think it's just a matter of writing the positives equal to negatives, right? Also making sure that you are accounting for the charge properly. So we've got, for example, 3 for the Fe3 plus, 2 for the calcium and magnesium, and so on. Okay, so pretty straightforward. We will make good use of this though, so it's the key is to recognize that when we are working with some sort of system, this has to hold true so we can use this as another fundamental equation. So if we're trying to solve for H plus and we can measure everything else, we can then know the acidity of a solution. Of course, it's usually easy just to stick a pH probe and find out that way. But if we had to calculate, let's say, what will our pHb if we add in all these things before we add them in, this is kind of the way to do it, or one way to approach it. That is a very challenging task. So if you're ever in a lab thinking about doing some chemistry and like, oh, I wonder what the pH will be if I add this, that, and the other, right? You'll see you have to know a lot of things, and then you have to know, okay, pretty careful understanding of the temperature and all of that. Okay, any questions, issues? Yeah.
Case for the HB.
Yeah.
We assume that it would dissociate like further, so we ended up having the H plus PS plus B2 minus. So with this example, why didn't we consider that for HSO4 and the other ions that were still complex?
Yeah. So why didn't we consider the H2B condition? Is that what you're saying? I think it kind of did that because it gave us sulfate and HSO4 minus, right? Because if we're taking this as H2SO4, it's a good question. H2SO4 will be in equilibrium with HSO4 minus plus an H plus, right? And so in that case, that is the HB minus, and that HB minus, HSO4, will be in equilibrium with SO4, sulfate, 2 minus plus H plus. But what we notice is the problem went ahead and gave us both sulfate and HSO4 minus. So in that sense, it did that for us already. And that's exactly what I was meaning when we started to take a look at it. And I said, hopefully you were thinking, oh, am I missing something? Do I need to do do some equilibrium reaction like that? But it just went ahead and gave it already. But that's a very good point, because if they gave us just this one and nothing else, maybe we have to have some prior knowledge here, but we would then know that, oh, we should also expect some sulfate. Or vice versa, if we had sulfate and we had some prior knowledge that this was also possible, would possibly show up, then we ought to know that, ought to include that. Okay, anything else? All right, this is all I have for you today. So next time we'll deal with kind of mass balance, proton balance, and start putting some pieces together. And I'll also get you a homework, I expect tonight or probably tomorrow. So, all right.